Welcome back, everybody. This is our fourth session in JEE Mains previous year questions for chapter Magnetism and Matter of class 12th. Before this video, we have made 3 videos in this series, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years. So if some of your friends are preparing for NEET, then they can find those videos in their dedicated playlist in channel's playlist section. If you find these videos useful, then do press the like button, share them, and subscribe to our channel. It will be a great help. And also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, let's start today's video. In the previous one, we were around 20, question number 20. So I think this was the last one which we covered. It was regarding a needle and the magnetic field. So let's now move to next question. Here it is. Bar magnet is demagnetized by inserting it inside a solenoid of this length, turns and carrying this current. Corrosivity of the bar magnet is. Now we have to find out corrosivity here, and we know that if we have a BH curve, we have B here, we have H here, and our curve looks like something like this. This is our BH curve. Now this term is known as corrosivity, and this term is known as retentivity. And we have a relation between both of these two. We know that from the relation that B is equal to mu naught times H. So we can use this relation. The value of B can be calculated using as B is produced. So it is produced by the solenoid, and for solenoid we know that B is equal to mu node Ni. Mu node N times I is equal to mu node H. Mu node get cancelled. Let me make it slightly more thick. Now coming to Ni, and here it is small n. Sorry, I wrote it capital N. Here it is small n. The difference between capital N and the small n is capital N is number of turns per unit length. In case of magnetic field, you get it small n. So it will be 100 divided by 0.2, number of units per meter, multiply current, that is 5.2 is equal to H. So it will be 100 by 2 into 10 into 52 by 10. 10 get cancelled, and we have 26 here is equal to H. So H comes out to be 26000 ampere meter. So option B will be the right answer here. Now let's move to the next one. Again, we have the same type of question. We have a BH curve for a ferromagnet shown in the figure. The ferromagnet is placed inside a long solenoid with 100 turns per centimeter. The current that should be passed in the solenoid to demagnetize the ferromagnet completely. Now, to demagnetize the material, after demagnetizing the material, its magnetic field should be equal to 0. As per asked in the question, that we need to find the current so that material gets demagnetized, and we know that when material is demagnetized, its net magnetic field will be 0. And in this graph, when magnetic field of the material is 0, these are the 2 points. When at this point magnetic field is 0 on this curve, and on this point magnetic field is 0, and on both of these points we get the value of H. So when B is equal to 0, then H is equal to 100. So we have to solve for this H is equal to 100, and the corresponding current that is required to produce H equal to 100 will be the required value of current that will be required to flow in the circuit, so that magnetic field of the material reduced to 0. Now we know that for a solenoid, B is equal to magnetic field is mu node N times I. And for the material, magnetizing material, B is mu node times H. Now comparing both of these, we get H is equal to N times I, and from this I is equal to H times N. Value of H is 100 and value of N, that is a number of turns per unit meter. We have been given number of turns per unit centimeter. So number of turns per unit centimeter are 10 raised to power 3, and number of turns per unit meter will be 10 raised to power 5. So it will be 10 raised to power 5, and from this current comes out to 10 raised to power minus 3 or 1 milliampere. Option B will be the right answer. Similarly, here direction of current need to be reversed, because as per the place we are starting, if we are starting from this place, then we will follow this curve. So here in this case, direction of current will be reversed, and if we are starting at this place, then we will follow this curve, then direction of the current will be the normal one, but amount will stay the same, 10 raised to power minus 3. Now let's move to next question. Hysteresis loop for two magnetic material A and B are given below. These materials are used to make magnets for electric generators, transformer cores, and electromagnet core. That then the proper use is. So we have to find the proper use, that which one of the following has a better use for either transformer or electrical generator. So now from this hysteresis loop, we know if we compare both of these two loops, we can easily say that loop A has larger area and loop B has smaller area. Now larger area means difficult to magnetize and difficult to demagnetize. Smaller area means easy to magnetize and easy to demagnetize. Now let's coming to the all the applications we have been asked. That first are electrical generators, then transformer core, and then electromagnet. Now in case of electric generators, what we need permanent magnets. And in case of transformer cores and electromagnet, we need temporary magnets. And if we are making a permanent magnet, then that permanent magnet should be able to retain its magnetic property under large reverse current, or we can say that magnet should has larger hysteresis loop area. So our material A or graph A satisfy this condition. So for electrical generator, we will use graph A, and for transformer cores and electromagnets, we need to magnetize them multiple times. And if we need to magnetize them multiple times, then this area is equal to energy loss in the whole process. So if we are magnetizing them multiple times, means we are losing energy every time, and we want to minimize that energy loss. For that, this area needs to be minimum, and that is good for transformer cores and electromagnets. That will happen in transformer cores and electromagnets, that we need a magnet such that it has a minimum energy loss, and for that option B will be a good viable option. So we can say A in case of generators, A case of generators, and so here it is mentioned in option A that A is for electrical generators and transformers. So this part is wrong. But in the B option, B is for electromagnetic and transformers, so B will be right answer here. Now let's move to next one. Okay, so we have a question here. A fighter plane of length 20 meter, length of plane is 20 meter, and wingspan, distance from tip of one wing to another tip, is 15 meter, and the height of the height is 5 meter, lying towards west over Delhi. Its speed is 240 meter. Earth's magnetic field over Delhi with declination angle of 0 degree and dip of theta such that sine theta is 2 by 3. If the voltage developed is VB between the lower and upper side of the plane and VW between the tips of the wings, then VB and VW are close to. So we have to find the value of voltage from the top to bottom and from the left to right for the plane. So first of all, let's draw the diagram. Let's first draw the directions. So suppose this is north, this is south, this is east, this is west, and we have a plane lying towards the east, means it is going towards the east. So we can say this is our plane, suppose. This is our plane. Now its wingspan. Wingspan means distance between these 2 points is given us around 15 meter. This distance is 15 meter, and height of the wings means this plane has certain height like this. So this distance is 5 meter, or what is it is? Yes, wingspan 15 meter, and yes, the height is 5 meter. This is 5 meter. So that's the basics of our plane. And its length is 20 meter. This length is 20 meter, and it is moving towards the east. And now coming to the direction of the magnetic field, it is mentioned that angle of declination is 0 degree, so we will ignore it. And dip angle is mentioned here. Angle of dip is such that sine theta is 2 by 3. So first of all, that resolve this, as mentioned that sine theta is 2 by 3. So we will make a triangle here. So this is theta, and sine theta is 2 by 3. So means this side is 2, this side is, this side is 2, this side is 3. So our base will be 9 minus 4 root 5. So from here, sine theta will be 2 by 3, and cos theta will be root 5 by 3. Now we know that in case of Earth, and that you need to remember that magnetic field actually moves from south to north. When we have a normal magnet, then magnetic field is from north pole to the south pole. That's that's everybody know for the Earth. But what we have for Earth, if suppose this is our Earth, and the upper hemisphere is northern hemisphere and the lower hemisphere is the southern hemisphere. So south pole of Earth is at this point. This is south pole of Earth in the northern hemisphere, and north pole of Earth is in the southern hemisphere. So magnetic We normally mark it as like north, and we normally mark it like as south. And magnetic field lines for magnet will be actually from north to south, but what will appear to us that they are moving from south direction to the north direction. So here the value here, this magnetic field with this angle of dip means our magnetic field is something like this. It is in both planes, means right now this field is going in the z plane and in the y plane, in the both of the planes, and one of its component will be along this south to north, and one of its component will be along in the downward in the plane of the paper. So let me draw it properly. It will be in the plane of the paper, and this is the angle theta here. So we have B here, and we will have B cos theta here, that will be in the south to north direction, and we will have B sin theta here, that will be going from top to the bottom of the paper, or going into the plane of the paper, B sin theta component. Now we will find the voltages, and voltages can be find that we know the EMF induced is given by B into L cross V. So as this B cos theta component, this B cos theta component is perpendicular to this 20-meter length. B cos theta component is perpendicular to 20-meter length. So there will be a potential, we can say potential difference across this 20-meter length, and also this B cos theta component is perpendicular to this 5-meter length. Let me clear it again, that this B cos theta component of the magnetic field, now if I make here directions, that will be easier. Suppose these are our coordinate direction, I, J, and K. So B cos theta is going in the y direction. B cos theta is in the y direction, and this 20-meter length is in the x direction. So both magnetic field and the length are perpendicular, and also this 5-meter length is in the z direction. So again, both magnetic field and the length both are perpendicular. So now the third component which we have to find, that is velocity, and it is given to be 240 meter per second. So velocity is 240 meter per second. Now in case of this 20-meter length, velocity and 20-meter length both are in the same direction, so they are parallel, so their cross product will be 0. So across 20-meter length there will be no actual potential development, but across 5-meter length, here velocity is in x direction, length is in z direction, and magnetic field is in the y direction. So there will be induced EMF, and so L cross V will be, here we will get, that is LV sin 90. So BLV will be the answer. So we can say EMF induced across 5-meter length will be B cos theta into L into V. Now value of B is already mentioned, that is 5 into 10 raised to power minus 5. Cos theta is root 5 by 3 into length is 5 and velocity is 240. Now solving this, we will get 44.72 into 10 raised to power minus 3 sorry, volts. So it will be around 45 millivolt. Now coming to the next component, that B sin theta. This b sine theta component is in the z direction, and here our 15-meter length is also is in the y direction. So this 15-meter length and b sine theta both are perpendicular, and again b sine theta is in z direction, and this 20-meter length that is in x direction. So here 15 and 20 both are perpendicular to b sine theta, but seeking from the direction of the velocity, this length 20-meter is parallel to velocity. So again in this 20-meter length there will be no potential drop, but along this 15-meter length there will be potential difference, because here velocity is in x, length is in y, and magnetic field in z. So all of these three are perpendicular to each other, so there will be a induced magnetic induced emf, and that emf in the 15-meter length will be given by b sine theta into length, that is 15, and into velocity, that is 240. So b is 5 into 10 raised to power minus 5. Sine theta is 2 by 3 into 15 into 240. So this will go to 5, and this will give us 120 into 10 raised to power minus 3 volts. So we got both of the values, 120 and 45. Now we have to find that which side on which side is on the higher potential, because we have two options which are matching. Option B is matching with 45 and 120, and option D is matching for us 45 and 120. Let's find out the that which side of the pilot will be on the higher voltage. So as we think know that this is moving towards the east, and if pilot is sitting here, then for this pilot, this direction, the this north one will be his left, and south direction will be his right hand side, assuming that pilot is looking towards the east. So his north will be for left for him, and right will be south will be right for him. Now let's find out the force on the electrons. According to that, we can solve that which side will be positive and which side will be negative. Now we know that force on a moving charge is given by Q V cross B. Now we assume that this plane is made of metal, and metal have lot of free electrons. So we will find the force on that electron, those electrons. Now charge on force is charge of electron is minus E. Their velocity, as all of the electrons are moving with the plane in the, we can say, x direction or in the east one, so we are making it like x direction. So I. Now coming to the magnetic field. Now let's see for this 15-meter length. For this 15-meter length, magnetic field is going into the plane of paper. Means in the negative z direction. So negative z direction means minus of k. So it will be E into I cross k, and that we know that I cross k is minus of j. So minus of j. So force on electron will be in the negative j direction, or in the downward direction here. So all of the electrons will come towards this right direction. So electrons will deposit here, and on the upper side we will have positive charge. So left hand side will be positive and the right hand side will be the negative. And from this we can say left hand side of the pilot at higher potential. So option D will be the right answer here. Let's move to the next one. Now in this question, a short bar magnet is placed in the magnetic meridian of the earth with north pole pointing north. that is north direction. Neutral point are found at a distance of 30 centimeter from the magnet on the east-west line drawn through the middle point of the magnet, the magnetic moment of the magnet in ampere close to. So we have to find out magnetic moment of the magnet. Now, first of all, let's draw the diagram for this. Suppose this is our Earth, and we have, this is our, we can say, equatorial line for Earth. Here, this is our, we can say, northern hemisphere, this is southern hemisphere, and for the magnet of the Earth, this is south pole and this is north pole. So let's place a magnet here. Suppose this is our magnet. Now we know that magnetic field lines due to Earth magnetism will move like this, as we are looking in the on the surface of the Earth, not inside of the Earth. On the surface of the Earth, magnetic field line due to magnet of the Earth will move from north to south pole. So these field lines will be moving like this. So they will have direction like this. And it is mentioned in the question that this magnet, the magnet which we place, is placed such like that its north pole towards north pole points towards the north of the Earth. Means this is the north pole of this magnet and this is the south pole of this magnet. For this magnet, magnetic field lines will move something like this. So they will be in this direction. So it means these magnetic field lines due to Earth and due to this magnet will cancel each other, and they will cancel each other at some point, and at that point we will get the, as mentioned in the question, what was that? Yes, a neutral point. So when these two fields will cancel each other, we will get a neutral point, and that neutral point is on the east-west line. So this line, that center line, is our east-west line. So suppose we are getting this neutral point here. At this point, both of these fields are cancelling each other. Now for this magnet, for this this small magnet which we placed, this is a equatorial point. This is a equatorial point. Now magnetic field due to this magnet at a equatorial point is given by mu naught by 4 pi into its magnetic dipole moment divided by the distance. This actually this is the distance, but normally we take this one, perpendicular distance, because these are comparable to each other as magnet is small. So this is the value of magnetic field. And horizontal component of Earth is already given, means value of this value of magnetic field due to Earth at this point is already given to us, that is 3.6 into 10 raised to power minus 5. So both of these fields are equal in magnitude, just opposite in direction at this point. So we will equate them. Now mu naught by 4 pi is 10 raised to power minus 7, m as it is. And now coming to the direction, the distance, that is 30 centimeters, so that will be 0.3 meter cube is equal to 3.6 into 10 raised to power minus 5. Solving this, we will get m is equal to 3.6 into 10 raised to power minus 5 into 3 into minus 1 cube, so 27 into 10 raised to power minus 3 divided by 10 raised to power minus 7. So that all in calculation, this is 10 raised to power minus 8, 10 raised to power plus 7, so 10 raised to power minus 1 into 27 into 3.6, that will be 97.2 into 10 raised to power minus 1, or 9.72. That is option C for us. So with this, we end this video here. Hopefully what we have covered till now is helpful to you, understandable to you. Again, if you have any doubt or suggestion, then you can put them in comment section. I will try to resolve them. And if you find these videos useful, helpful, then do press the like button, share it, and subscribe to our channel. Also, if you like to make a small financial help to us, then you can scan any of these QR codes in front of your screen and donate us any amount. With this, again, thanks for watching, and we will meet in next video.